Now that we understand the concept of symmetry and reflection, we're going to look at how we can extend that to the definition of an even function or an odd function. So I'll fill in the blanks first, and then we'll unpack why it should make sense based on what we have just previously gone over. Even in odd functions, a function f is called an even function if, let me write it out, if when you plug in a negative x, in other words, if you change the sign of x, your y value will be the same as if you did not change the sign of x. In other words, let's see what that looks like. If I have a point x, comma, y, and we know y is another way of saying f of x. So another way I could write that is x, comma, f of x. If I have a point xy on a function, and then I put a negative x in and get the same y value, or in other words, when I use negative x, the y value is the same. In other words, these two y values are going to be the same, even though the x sign is different. Okay? That means it is symmetric to the y-axis. Okay? And we just tested for y-axis symmetry, and when we did, we plugged in a negative x and then simplified to see if we could get back to the original f of x. Then the next part says, a function f is called odd if, when we plug in a negative x, or if we change the sign of x, or if we try to move across the x-axis, then we also have to move across the y-axis so that the y value also becomes a negative, or a different sign. So what does that look like? That looks like we have x, comma, y, and then when we try to do negative x over here, we do not get the same vertical location. Instead, we get this almost the same location, except for it's on the opposite side of the x-axis. All right. So what happened with that is we're actually symmetric to the origin. Flipped it upside down, and you flipped it like turning a page, and then you were over here in this quadrant, or you had both on here. So like a good one that is to look at that is symmetric to the origin is the cubing function, because if you flip it upside down and you flip it across the let me say that again. If you flip it upside down, it's not going to look the same. If you just flip it upside down, it won't look the same, right? Also, if you just flip it across the x-axis, it won't look the same. However, if you flip it across both axes, so you flip it here and then you flip it here, it does look the same. So that's if you have a function that is symmetric to the x-axis and symmetric to the y-axis, such as like a circle centered at the origin, okay, this is an example of an equation that would be symmetric to both the x-axis and the y-axis. It is also symmetric to the origin. Right, so you have this connection, you have this connection, and you have this connection. So it is true that equations which have both x-axis symmetry and y-axis symmetry, those are symmetric to the origin. But it does not work the other direction. The converse is not also true. So what I mean is you can have origin symmetry, such as with the cubing function. This is origin symmetric, or symmetric to the origin, right? But it is not symmetric to the y-axis, neither is it symmetric to the x-axis, right? So you can say if an equation is symmetric to the x-axis and symmetric to the y-axis, then it has origin symmetry. However, you cannot say that if an equation has origin symmetry, then it must be symmetric to both the x-axis and the y-axis. It might be, but you can't automatically make that assumption. All right, so a function f is called odd if, whenever you change the sign of x, you are forced to also change the sign of y in order to stay on the function's graph. In other words, it is symmetric to the origin. All right, so classroom example number 5, determining whether functions are even, odd, or neither. So I'm going to see if g of x is symmetric to the y-axis, because if it is, then it's even. So let's see. To see if it's symmetric to the y-axis, I want to see if when I change the sign of x, if I still get the same function value. All right, so let's see what happens. A negative raised to an odd power will have a negative result. So this is going to be negative x to the 5th, and a negative to an odd power again, so, and then it's going to be times this positive 2. So this part will have a negative result, and then it's going to be multiplied times this positive, so that's going to result in negative 2x cubed. And this right here is going to be positive 3x. So let's see if g of negative x is the same as g of x. Okay, so we can see there's a negative here, there's a positive here, so that's not the same. Negative here, positive here, not the same. Positive here, negative here, not the same. So this thing is not symmetric to the y-axis, and it is not even. Okay, so A is not even. However, but it is odd. And how I know that is because every single sign is different than the original. And to illustrate that, if I factor out a negative right here, then I will have positive x5 plus 2x cubed and negative 3x. So literally, my g of negative x results in the original g of x with a negative out front, which is exactly what we said had to be true. If you plug in a negative x, then you have to have the same function value except the whole thing is negative. Or in other words, every single term is the opposite sign. All right, so let's look at, so I'll write this down here. G of negative x is negative x to the 5th plus 2x cubed minus 3 of x and this whole thing is g of x, so we can conclude that g of negative x is equal to negative g of x. So it's odd. Okay, so now we'll do b. H of negative x is equal to 2 negative x quantity squared minus 3. When I simplify this, the negative x times a negative x will be a positive x, so I'll get 2x squared minus 3. So h of negative x is actually the same as regular h of x. So this is even. Right, now it's only going to be one or the other. So if you discover that it's even, it's odd. I meant to say, obviously, if you discover it's even, then it isn't odd. You don't have to do 2 tests. So when you're testing for even or odd, you do one step only. Right, so with symmetry, when we're testing for symmetry, remember what we had to do is we had to replace y with a negative y and see if we got back the same thing, and we also had to replace x with negative x and see if we got back the same thing. So we had 2 different things to do there, and it is possible for a function to have x-axis symmetry and y-axis symmetry. So it wasn't like we could figure out, oh, it has x-axis symmetry, then automatically we know it doesn't have y-axis symmetry. That's not true. It could still be possible, so you have to do both tests every time. But the nice thing with even and odd testing is that you're doing only you're only having to do one step in order to determine whether it is even or odd or neither. The only thing you have to do is plug in a negative x and simplify it. All right, so the next part C, k of negative x. All right, so I'm just plugging in a negative everywhere. Negative x there, negative x there. Then simplifying, this becomes a positive x squared, negative 6x. The 9 stays the same sign. So k of negative x, well, it's not equal to k of x, the original, because this sign is different here. And it's also not equal to negative k of x, because if it was, then every single sign would have changed, and the first term's sign is still positive, and the last term's sign is also still the same. So you have to have all of the terms stay the same sign, and that would mean it's even, or all of the terms change sign, and that would mean it's odd. But if you have a little bit of both, then it's neither. Okay, so this one was odd, this one was even, and this one was neither.